Welcome to The Explainer. Today, we're going way back to the very beginning of artificial intelligence. We're going to build the first thinking machine from scratch, a single, simple artificial neuron that, believe it or not, sparked the entire AI revolution we're living through today. We're talking about the Rosenblatt Perceptron. All right, here's the game plan. First, we'll look at the biological inspiration, the brain itself. Then we'll actually build our artificial neuron, the perceptron. We're going to teach it, find out what it can't do, and then see how overcoming that one tiny limitation unlocked, well, everything we know as deep learning today. So, if you want to build an artificial brain, where do you start? Well, it probably helps to look at the blueprint of a real one, right? The pioneers of AI weren't just thinking about code, they were looking right at neuroscience, trying to figure out how to copy the most powerful computer on the planet, the one inside our own heads. Okay, so this is a real biological neuron. It's the basic building block of you, me, and all of our thoughts. You've got these little branches called dendrites that collect signals from other neurons. All those signals get summed up in the cell body, and here's the key part. If the total signal is strong enough, if it crosses a certain threshold, the neuron fires. It sends a single, all-or-nothing electrical pulse down its axon to other neurons. It's a simple yes or no decision. Is there enough stimulation or isn't there? Now, what is so cool about this, and you can see it right here, is how literally this biological idea was copied into a machine. This wasn't some loose metaphor, it was a direct translation. The dendrites became inputs, the cell body became a little math unit, and the axon became the single output. It's a really beautiful and simple idea. So, with that biological blueprint fresh in our minds, let's actually build our first artificial neuron, the perceptron. And there it is, the Rosenblatt perceptron. I know, it looks pretty simple, but this little diagram is the great-great-grandfather of ChatGPT and everything else. Here's how it works. It takes a bunch of numbers as inputs, we'll call them X. Each one of those inputs gets multiplied by a special number called a weight, that's our W. You can think of each weight as a volume knob for its input. Once all the inputs are multiplied by their weights, you just add them all up. That's it. These weights, they are everything. This is where the learning happens. A big positive weight means its input is really important for making the neuron fire. A big negative weight means its input is really important for stopping the neuron from firing. And a weight near zero? Well, it means a neuron just doesn't really care about that input. The weights are the strength of each connection, just like some connections in your brain are stronger than others. Then you've got this little oddball, the bias. It's basically a free-floating weight that isn't attached to any specific input. It just gets added to the total sum no matter what. You can think of the bias as the neuron's personality. Is it optimistic or pessimistic? A big positive bias means the neuron is kind of trigger-happy, ready to fire with just a little push. A big negative bias means it's very skeptical and needs a ton of evidence before it'll fire. Okay, so the perceptron has done all its math. It's multiplied the inputs by the weights, added them all up along with the bias, and now it has one single number. But a neuron has to make a choice: fire or don't fire. That final decision is made by something called an activation function. It takes that final sum and decides the output. The original perceptron used the simplest decision maker you can imagine, the sign function. It's a hard line in the sand. If the final sum is positive or even just zero, it fires, bang, output is +1. If the sum is negative, it stays quiet, output is -1. It's a yes or no world for the perceptron, no maybes. And this is where it gets really, really cool. With the right set of weights, this single little neuron can act like a fundamental piece of a computer, a NAND gate. Check out that last row. Only when both inputs are true, or +1, does the final sum dip just barely into the negatives, causing the neuron to output false. Any other combination, and it outputs true. This was huge. It proved that these simple brain-inspired things could perform real, formal logic, the same stuff that powers every computer on Earth. But figuring out those weights by hand for a NAND gate is one thing. The real magic, the reason this changed the world, was figuring out how the perceptron could find the right weights all by itself. We don't program it, we teach it. And this is how it learns. It's called supervised learning because we, the supervisors, give it the right answers to learn from. It's actually super intuitive. You start with totally random weights. The neuron is a blank slate. It knows nothing. You show it an example. It makes a guess. If it gets it wrong, you just nudge the weights a tiny, tiny bit in a direction that would have made the answer a little more correct. And you just repeat over and over and over until it stops making mistakes. And you can literally watch this happen. Our goal here is to draw a line that separates the pluses from the minuses. The first red line, that's our random starting point, is obviously wrong. But every time it messes up, the algorithm nudges the weights and the line moves a little. You can see it shift from red to purple to yellow, getting a little bit better each time, until finally that solid blue line perfectly separates the two groups. Learning complete. So here's the big takeaway. A single perceptron can learn to draw a single straight line, or a flat plane in more dimensions, to divide two groups of things. If your problem can be solved with one straight line, we call that linearly separable, and a perceptron can totally master it. This was a massive success. But this amazing success also revealed a massive, massive weakness. It begs the question, what happens if your problem can't be solved with just one straight line? This very question led to a problem so famous it nearly killed the entire field of AI research for about a decade. People call it the first AI winter. And the problem's name is XOR. It stands for exclusive OR, meaning one thing is true or the other is true, but not both. It's a dead simple idea, but as it turns out, a single perceptron is completely powerless against. Just look at this. The pluses and minuses are in this checkerboard pattern. Go ahead, try to draw one single straight line that puts all the pluses on one side and all the minuses on the other. You can't. It's impossible. And the perceptron can't do it either. These images show it trying. The line just thrashes around like crazy, back and forth forever, never finding an answer, because for a single perceptron, a correct answer simply does not exist. This failure was so profound, it convinced a lot of people that this whole idea was a dead end. For years, this XOR problem was seen as a fatal flaw. But the solution wasn't to invent some kind of super complicated new neuron. The answer, it turns out, was beautifully simple. Just use more of them. Think about it. If one line can't do the job, what if we use two? With two lines, you can easily fence off any region you want. This idea, combining the power of multiple simple line drawers, is the absolute foundation of all modern AI. The power isn't in the neuron, it's in the network. So, here's how we build it. You have your input layer, no big deal, but then you have a hidden layer. Here we put two perceptrons. You can think of one perceptron's job as learning to draw one of the lines, and the other perceptron's job as learning the other line. Then the final output layer has one last perceptron. Its job isn't to look at the original data, but to look at the answers from the hidden layer. It learns a simple rule like, if the point is above line 1 and below line 2, then the answer is true. And just like that, you've built a real neural network. This structure, input, hidden layers, output, is the exact same blueprint used in the giant AI models we have today. The only difference, really, is scale. Instead of two neurons in a hidden layer, they might have billions, stacked in hundreds of layers. But the core idea is exactly the same. Simple things, working together, create complex intelligence. Okay, so stacking these neurons gives them more power, but how on earth do networks with billions of them run so fast? Going through them one by one would take forever. The secret isn't just faster computers, it's smarter math. On the left, you see the slow way you might code this up, a loop that goes through each input and weight one at a time. It works, but it's painfully slow. On the right is how it's actually done. We take all the inputs and bundle them into a thing called a vector, and we do the same for the weights. Then we can do that entire weighted sum calculation in one single, super fast operation. That one operation is called a dot product. And what's amazing is that it lets us do all the little multiplication and addition steps at the same time, in parallel. This is exactly what the GPUs in gaming computers are built for. By speaking the language of linear algebra, of vectors and matrices, we can run these calculations at lightning speed, making networks with billions of neurons possible. And this math gives us a much cooler way to picture what's happening. A perceptron with two inputs isn't just drawing a 2D line. It's actually defining a flat plane in 3D space. The two flat axes are your inputs, and the vertical axis is that final weighted sum. The neuron's final decision is just based on whether your data point lands above or below that plane. Learning is just the process of tilting and shifting this plane around until it perfectly separates your data. So when you boil it all down, the journey from this simple line drawer to the crazy AI we have today wasn't about inventing a single, perfect, super smart neuron. It was about realizing that the solution to a hard problem might just be more simple neurons arranged in another layer. And that leaves us with the big, exciting question that still drives AI research today. What other problems that seem impossible right now will turn out to be solvable just by adding another layer?